Hi guys, in this video we're going to be talking about three-dimensional lines and how we can define them using vectors. So first of all, before we do that, I just want to revise a couple of key concepts. So first of all, I just want to think about scalar multiplication and what it means for a vector. So let's say we've got some vector sitting here that I'm going to call A. And we multiply it by a value. So we're going to do a scalar multiplication. So this is where we do like k multiplied by a. Well, what does that mean in terms of the vector itself? We know that if we do k multiplied by a, and a is a1, a2, a3, then that's equal to a vector ka1, ka2, ka3. So what it's doing is it's multiplying every component in the vector by the same value. And if we visualize what that means, let's say k was 2. What that means is that the vector is going to go in the same direction, but it's going to be twice the length. So this would be 2 multiplied by a. What if k was a third? Well, it would be a third of the length of a. So that in there would be a third multiplied by a. And if if k happens to be a negative value, then we would find that it actually goes in the opposite direction. So let's say this one was negative 3 over 2 multiplied by a. Its length is multiplied by 3 over 2, so about 1.5 times the length, and then the direction is in the reverse. So that's what scalar multiplication means for a vector, and this will be important in a minute. The other thing I just want to quickly revise is this idea of a vector from the origin. So let's say we've got a point in space with coordinates x, y, z, and we've got the origin down here, which is 0, 0, 0, and we're going to connect the two. Not a great drawing there, but we're going to connect the two with a vector, which I'm going to call OP. The coordinates of that the components of that vector are just going to be the exact numbers in P. So when we talk about a vector from the origin, we're really just saying it's a vector with the components given by that point, and that will be important in a moment too. Okay, let's move on. Okay, so let's have a think about lines in 3D. Well, before that, let's just quickly revisit lines in 2D. So if we're looking at 2D lines, you guys know that we have an x and a y axis. And if we've got a line in 2D, we normally say that the equation is something like y equals mx plus c. However, if we've got an equation in 3D, it gets a little bit more complicated. So we've got a z-axis and an x and a y. But that line could really be going anywhere through space in that three-dimensional plane. So it's not quite as easy as what we did with 2D. But let's think about how we can deal with this. So what I'm going to draw up here is this is the line that we're interested in. So it's a line through space that continues forever and ever and ever. Down here I'm going to draw the origin, which just has coordinates 0, 0, 0. And there's going to have to be two things that we know about this line if we're going to define it. First of all, we need to know a point on the line, which I'm going to call A. And A has the coordinates A1, A2, and A3. So that's a point that we know is on the line. Somewhere up here, we're going to say this is just any point on the line. Any old point, doesn't matter. This is the point that kind of moves up and down the line to define everything that's on it. And we're going to call that point R, okay, capital R. And capital R is going to have coordinates X, Y, and Z, okay, because that's defining the line. So what can I do now? Well, let's think back to our vectors from the origin. So I'm going to draw my first vector, which goes from O up to A, and I'm just going to call that little a, vector little a. Now, the other thing I'm going to do is draw a vector from O up to R, and we're just going to call that little r. So little r can be pointing at anywhere on the line. Little a is pointing at a specific point on the line. Now, the other thing that we need to know for this to work is we need to know some sort of vector that tells us the direction of the line. So this is a vector that points us in the right direction. So if you can imagine, you define the line by going to a specific point on the line and then shooting along the line in the direction of this vector, which I'm going to call lowercase b. Okay, so what we can say is, to get to capital R, which is anywhere on the line, so that's our vector little r, what we're going to do is we're going to travel along the vector A, and then we're going to travel using the vector B, but we don't know how far we're going to have to go. We're going to have to go in the direction of B, but we don't know whether we're going to have to keep going all the way up here, or maybe back here somewhere, or even further. So what we're going to do is we're just going to multiply the vector B by this scalar that we call lambda. And lambda basically controls how far along the line we go. So if lambda is 1, we've only gone to this point here. If lambda is 2, maybe we'd end up at this point. If lambda was 3, we'd end up at this point. If lambda was negative, we'd end up down here somewhere, and we can move anywhere along the line. Another way of thinking about that, if we write these out, is that the vector little r is going to be the components of big R, which is x, y, z, and that's going to be equal to the components of A, which is A1, A2, A3, plus lambda, and I'm going to say that the components of B are B1, B2, B3. Now, if we take this, this vector equation, what we can do is actually expand that out, and I'll show you how to do that in the next example. Okay, so here's an example. We've got a coordinate, which we've called A, and A has x, y, and z components, -1, 0, and 4, and it's on a line with a direction vector given by 2i take 3, that should be 3j plus k. So that's defined using the unit vectors, just to be a bit tricky. And we want to find the vector equation for the line, the parametric equation, and the Cartesian equations. And I'll explain what they are in just a moment. So first of all, for our vector equation, what we're going to say is that r equals little a plus lambda times b, and in this case that means that r, which is x, y, z, equals little a. Little a is the vector to big A, which is -1, 0, 4. So that gets us to our starting point, plus lambda multiplied by our direction vector. Now in this case, the direction vector, B, has the components defined by I, j, and k. So it's going to be 2, -3, and 1. Okay, so that's just come straight out of here. So we can put these back in, 2, -3, and 1. So this here is our vector equation, and we should add that lambda is any real number. Now we need to find our parametric equation. So parametric equation just basically means taking each of the components. So we're going to take the first component and say that x equals -1 plus lambda multiplied by 2, or 2 lambda. The second component, y, is going to be equal to 0 plus lambda multiplied by -3, or -3 lambda. And z is going to be equal to 4 plus 1 lot of lambda, which is just 4 plus lambda. So what we've done here are what we call the parametric equations. So instead of writing it out as vectors, we've written it out as x equals, y equals, and z equals. Now the last one that we want to do is the Cartesian equations. Now what we're going to do for that is we're going to say, note that if we rearrange each of the parametric equations for lambda equals, the first one can be rearranged to say that lambda equals x plus 1 divided by 2. The second one tells us that lambda equals y over -3. And the third one says that lambda equals z take 4. So I've just taken the three parametric equations, 1, 2, 3, and rearranged them to be lambda equals. Now what I'm going to do is I'm going to say if lambda equals all of those, then they must all be equal to each other. So x plus 1 over 2 equals y over -3, and that equals z take 4. And this is what we call our Cartesian equation for the line. So the Cartesian equation is just in terms of x, y, and z. There's no lambda. You'll find the Cartesian equations aren't used particularly often. What's probably used most often are these parametric equations here. Okay, I hope that helps, and thank you for watching.